Start video. Recording. Well, let's see. We've got Daniel and Nathan so far. That's good.
How you doing this morning, Professor?
Yeah. Hello. Hello there, Nathan.
Good to see you.
I'm sorry?
I said good to see you.
Yeah, good to see you. Yeah. Good to see you, man. On this rainy day. It's raining here. How about there?
Yes,
There's
very
Bryce.
rainy.
How about you, Bryce? Is it raining at your place?
I can't see outside, but last time I checked, it was raining.
Yeah. Well, it's raining here. Okay, let's see who else we got here. We've got a good crowd. Nicholas, Nathan, Daniel, Bryce. Whoops. Muhammad, Julian, William. We've got a pretty good crowd here. William, Nicholas, Nathan, Julian, Bryce. The topic today, let me write that down. The topic is polytropic processes. But before we begin, did anybody have anything they wanted me to do or have a question for me? The floor is open for your questions. Well, I don't hear any questions. You're not muted though. Let me see here. You can unmute and say hello if you have any questions. Okay, nobody has any questions. We're going to talk about polytropic processes. Let's see if I can find it here in the book. Maybe you can find it for me. Aha. I find it in the book on page 72. It's on page 72. Now we've talked about processes before. We've talked about processes. We've talked about isobaric processes, isochoric processes, isothermal processes. I don't know if I've told you about adiabatic processes or not. Adiabatic process. Have I? Hey, No, Bryce says no. So we probably haven't. But what that is when there's no heat transfer. There's no heat transfer. That's supposed to say no. N-O. Anyway, there's no heat transfer. I wonder if we've done any other kind of processes. I can't think of any. But there's a million processes. It's kind of like, how do you get from your house to Walmart? Well, you probably go the same way every day. You know, we're creatures of habit. But you could go a different way. There's more than one street you could go down, and you could turn left instead of right and so forth. And you could still wind up at Walmart, couldn't you? There's more than one path to get to wherever you want to go to. Yeah. Well, today we're talking about polytropic processes. What that is, it's sort of a curve fitting thing. You can fit 1,000 different paths or processes into a polytropic equation. And here it is. Let's give you the equation for a polytropic process. It goes like this. PV to the n equals some kind of constant. That's it. You're looking at it. It's on page 72. This n here, this whole thing here is called the polytropic equation. Polytropic equation. Or some people call it the polytropic condition. You could call it the polytropic condition. That little n there has got a name. It's called the polytropic constant. Polytropic constant. And it could be anything from minus infinity to plus infinity. That covers a lot of ground, you know it? It can even be zero. Now, like for instance, if it's zero, if n equals zero, then what you have is PV to the zero equals K. Now, V to the zero, anything to the zero is just one. So you just have P times one equals some constant. Hey, that's an isobar, you know it? If P is equal to some constant, they call that an isobar. So polytropic constant will fit an isobar. Yeah, no problem. Now, if the polytropic constant is equal to 1, then PV to the 1 equals a constant. Now, we've seen something like that before. If you had a constant temperature, then this constant could be R, which is a constant, times T, which is a constant. Hey, you know what you're looking at there? You're looking at an ideal gas isotherm, aren't you? Here, let's plot those up. Do I have room here? Yeah, I have room. Suppose this is your PV here. And you're going to go from state 1 along an isobar to state 2. Well, you know what the polytropic constant is? It's 0 for an isobar. We just talked about that. See, when this is an isobar. Now, if n equals 1, let me draw your isotherms in here. You know, an ideal gas isotherm kind of looks like that. That's your isotherm. So you could go from 1 to 2 up here. Well, we hate to go 2. 2 is there. How about 3? We'll go from 1 to 3 up here someplace. There we go. That could be state 3. We followed an isotherm. You know what? That's a polytropic process where n is equal to 1. What if we went somewhere in between? Let's say we go to state 4, from 1 to 4, and we come up here someplace, and this is state 4. N would have to be something between 0 and 1. How about maybe, I don't know, 0.5 or 0.6, or can you see you could have a 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.75. You could have a million things in there. Hey, how about this? What if you came up here to state 5? Here we go. Let's put state 5 right here. What would be the polytropic constant number for going to state 5? You need to put your little arrowheads on there. How about a, I don't know, 1.5, or it could be a 2 or 3 even, huh? 4 or 5. Yeah. Now, how about this? This one here is n equals 0. What if you came down here, call this state 6? What would be a value that you could go down there on your polytropic process? Well, it'd have to be negative, wouldn't it? It would have to be negative. You could have a negative, I don't know, there's a million and one negative, you have negative 1.5 or something like that. Do you see this as a curve fitting thing? We can fit thousands of processes with this polytropic equation. Now, that doesn't mean that every process can be fitted with a polytropic equation. No, there's processes that you can't fit with a polytropic equation, but you can fit an infinite number. If you understand that, we're going to go on and calculate the work done by polytropic processes. Any questions so far? Well, okay. Now this is all in your book. In fact, it's on page 72. So if you want to tune me out, go ahead, tune me out. You could read your book, but I'll go through it here because it's important. We got to know how to do this. Now, you know the definition of work. Well, there's a big W that goes like this. I think I explained this one day. If you don't understand it, just speak up. But we're going to go with little w's. I like the little letters better. That's the work per mass. And it's the area under your PV diagram. Okay. We know that. We've studied that. We know that if you have a PV diagram, say you go from 1 to 2 maybe. There's 2. State 2. The area underneath this diagram is the work per mass. You could color it in if you wanted to. There you go. Yeah. All right. Now we're going to do some algebra and come up with some equations. Then we're going to do some problems. That'd be good. Now, the polytropic equation goes like this. PV equals PV to the n equals some constant. So can you get to here with me? P equals that constant divided by v to the n. Can you make it from here to here? Well, let's plug it in. So that'd be the integral of k over v to the n dv. All right. Now go back to this here for just a minute. You could go P1 V1 to the n would equal to P2 V2 to the n would equal to P3 V3 to the n would equal to dot, dot, dot forever and ever, and which would equal your k. So all of these equal to the k. And we got a nice equation here now for our work per mass. Only I'm going to write it like this: k v to the minus n dv. All right. And now we want to go from v1 to v2. Okay. Now, when you integrate this, you could pull the k out. It's just a constant. And when you integrate that, I get v to the minus n plus 1 divided by minus n plus 1. Now, if I lost anybody, just speak up. Now, the thing is, you got to put in these units. Okay, we're almost done, and we're going to have the work of a polytropic process, which includes thousands of different processes. So that k, we're going to plug in the V2 there. I tell you what, I think I'm just going to call that k P2 V2 to the n. That's what k is equal to. So I get P2 V2 to the n times V2 to the minus n plus 1 divided by minus n plus 1. Then I have to subtract, and that k is also equal to P1 V1 to the n, so I'm going to write it like that: P1 V1 to the n times V1 to the minus n plus 1 divided by your minus n plus 1. Almost done. There's the last step. Guys, when you multiply, you add the exponents algebraically, and you know what you get? You get P2 V2 minus P1 V1 all over 1 minus n. Da-da, bottom line. Box it up. Important equation. It's the equation for polytropic work per mass. You'll see it in your book on page 72. Only they did it in big letters. If you want big letters, it's P2 big V2 minus P1 big V1 all over 1 minus n. That's what they have in the book on page 72. If you want work per mass, which is more valuable to us, there it is. Ta-da! We have just cooked up the wonderful equation for polytropic work. Any questions so far? Well, I didn't hear any, which means that either we understand this so well we don't even need to ask questions, or it could mean that we don't have a clue of what's going on and we know nothing. I hope it's the first one. Now here's a teeny tiny problem. What if n is equal to 1? I was telling you that n could be 1. In fact, it is for an isotherm with an ideal gas. We did that a little bit earlier. Those of you that were awake, look at your notes there, or hey, you could watch the video again. Yeah, n could be 1, but see, there's a problem. If n is equal to 1, we have a 0 in the denominator, and that's bad. Mathematicians have a hissy fit when that happens. They just kind of go nuts. So what do you do if n equals to 1? Well, here, let's show you. We got this equation. We're going to keep it. I'm just going to make a little room here. This is all on page 72. It might be on 73. No, it's on 72. It's all on page 72. Now what we're going to do is, what happens if n equals 1? Well, if n equals 1, you still got this polytropic condition. It's just that the polytropic constant is 1. And so the work per mass will be P delta V. But see, you could write P as K over V, delta V, from V1 to V2. Can you get to there with me? If not, speak up. Well, we took this in school. This is equal to K natural log of V when you plug in these limits. And that's equal to K natural log of V2 minus the natural log of V1. And that's equal to K natural log of V2 over V1. Okay. I think, boy, Juve, I think we're done. Except remember what that K is. K in this case is equal to P1 V1 to the 1, which is equal to P2 V2 to the 1, which is equal to blah, blah, blah forever. So we could write this as P1 V1 natural log of V2 over V1. And we have our second equation. Ta-da! Now this is when n is equal to 1. This one here is for when n is not equal to 1. We've got the equations. We have our polytropic work equations now. And we're ready to work problems. Did you have a comment or question? Okay, we're going to work problems now. Here goes. I just need some room. We're going to do problem 3105 together. I'll just say goodbye to all this. And look up problem 3105. I'm looking for it here. Okay, it's air. Air goes through a polytropic process with n equals 1.3. Well, let me write some of this down. We're dealing with air. N is equal to 1.3. In a piston cylinder, it starts at 2200 kilopascals and ends with a pressure of 200. You know what? The pressure went down, didn't it? let's draw a device sketch. Don't we always do a device sketch? Well, yeah, we always do a device sketch. Pressure went down. We're starting off with a pretty high pressure. Let's put some heavy weight on here. I think we're going to take that weight off. And I think that when you take the weight off, that makes sense to me. And they said, and it starts off at 2,200 kilopascals. This is state 1. This is state 2. This is 2,200 kilopascals. And it ends up 200 kilopascal. Took that weight off. Now this was 1,800 K. 1,800 K. And I don't know if you know this, but when you take that weight off and it expands, it usually cools off. I think it's going to cool off. You see, the opposite, when you compress, when you take air and you compress it, like with a bicycle pump, did you know that that air gets hotter when you compress it? You compress a gas, it gets hotter. Well, when you expand a gas, it gets colder. So I don't know the new temperature. Why don't we just say T2 for now? But I get the feeling it's colder. Let's draw a PV diagram. Isn't this how we do our problems? Don't we do a device sketch and a PV diagram and the first law, and we'll learn the second law in a while. And now we've just stumbled onto another lovely equation called the polytropic equation, but we can use that. So here, let me put some isotherms on here. We know what isotherms look like with air. They kind of go like that and like that. I think we're getting colder. See, these are not here. These are hot and these are cold. So we're going from hot to cold and the pressure is going down. I think we're doing this. We're at state 1, and we're going to state 2 at a lower temperature. This one here would be the 1,800 Kelvin. We don't know what T2 is yet. Now, do you remember if we came over here at constant pressure, the polytropic constant is 0. Now, if we came down here on the isotherm, the polytropic constant is 1. So our process that we have, well, look at there, it's 1.3. Well, that makes sense. See, if this is 0 and this is 1, then 1.3 would be kind of down there. Yeah, kind of makes sense. Okay. Well, let's write the polytropic equation. It goes like this: P1V1 1.3, P2V2 1.3. Great. Well, do we know what P1 is? Well, yeah. Do we know what V1 is? Well, no, but we could get it. We certainly could get it. Because P1V1 is equal to RT1. Now we know P1. We know R and we know T1. We can get V1. I'm going to shut up now. And I'll give you a minute and a half if you need it. I need Little V1. We're going to get little V1 here. Go ahead. And then I'll call on one of my brightest students here in just a little bit. Go for it. I know you can do this. Okay, well, let me call on one of my students here. How about my friend William? William, unmute and say hello, please.
Hello?
Hello. William, did you get the specific volume at state one?
I have not yet.
Now take your time. Do you need any help doing that, William, or you think you can do it?
I got it. It was just taking a while to find
Yeah.
the table.
Go ahead. Yeah, go ahead. William, this R here is 0.287. Is that what you're looking up?
Yeah.
Memorize that, William.
All right.
Memorize that. Then you won't have to look it up all the time. Save yourself some time.
For the volume,
William, what'd you get?
0.2348.
That's what I got. 0.2348 cubic meters per kilogram. Good going, William. Proud of you. Hey, look at here. We just got that. Yay, look at us. Now, we know P2, don't we? Isn't that nice? Hey, look at this equation. We know everything in here except V2. See it? Here, let me mark that on my diagram here. Here's V1. V1 is 0.2348. And V2, well, we're going to get V2. We know all this. Plug it in. Again, I'm going to shut up for a tiny minute. And then I'll call on another student. I won't pick on William again this time. And then find V2. Go for it. I know you can do this. Well, I got an answer for V2. I wonder if anybody else did. How about my friend Reagan? Reagan, unmute and say hi, please.
Hi, I'm a little bit close. I'm still.
He's close. We'll wait. We'll wait, Reagan. I think I know the answer. Reagan, how's it coming?
Yeah, almost close, sir. I think I'm getting the wrong answer. I'm getting 0.28.
No, that's not right. It's going to be bigger than 0.23. See, the volume gets bigger.
Yeah, that's what I'm thinking. I'm trying to find out what exactly I did wrong.
Well, maybe I should go through it. Here, let me just go through it with you. Now, what I'm coming up with is 1.4853. Did anybody get that? If you did, say, uh-huh.
Uh-huh.
Yeah, there, I heard two uh-huhs. Good. Well, here, let's go through that. We got to know how to do that. I just need some room here someplace. There's quite a bit of room right here. I bet I can do it here. Yeah, we got some room here. Okay, P1 is 2200. V1 is 0.2348, and you put that to the 1.3. And P2 is 200. And there's V2 1.3. Now, I know you can do all that and divide by 200, and that's what I'm going to do. And I'm going to get all that. So let me do that. Hang on. 2200 times 0.2348, 1.3 divided by 200. Okay, here's what I'm getting. Now, I'll go through that slowly if you still aren't happy with it. But I'm getting, I just divided 200 into these when you multiply them. Then there's several ways to go from here. It's just math, and I know you've studied this. One way is to go the natural log of 1.67225 equals the natural log of V2 to the 1.3. But see, that's equal to 1.3 times the natural log of V2. So what I'm going to do is I'm going to take the natural log of this, and then I'm going to divide by 1.3. And here's what I've got in my calculator right now. 0.39551 equals the natural log of V2. This is one way to do this. Then what you do is you hit the anti-log button. That's the little e to the x button. It's sort of the reverse of the natural log. So I'm going to do that now. I'm going to go shift e to the x, and boy Jove, you get V2 is equal to 1.485. Well, that you can round off, but that's good enough. Cubic meters per kilogram. Ta-da! That's one way to get it. Okay, now we've got V2. V2 is 1.485 with some numbers there. I want to get T2. Remember, it's going to be colder, we think. How are we going to do that? Well, look at here. P2V2 is equal to RT2. And we know P2. And we just got V2. And we memorized R. We've memorized R. So I'm going to again shut up for a minute. And I want you guys to give me T2. And I'll call on one of you here in just a minute. Find T2 for me. We're trying to find T2. And I'm going to ask Nicholas. Nicholas, unmute and say hello.
Hello.
Yeah. Hey, Nicholas, did you get T2?
Is it 1035?
That's what I got. I'm getting
Kelvin?
T2 is 1035 Kelvin. Hey, it cooled off, didn't it? It went from 1800 Kelvin to 1035 Kelvin. T2 is 1035 Kelvin. See, and V2 is 1.4853. Look, we can put a lot of information on there. But now what I think they want us to do is to find the work. Now the work is the area under this graph. They want the little w. I think they also want the heat transfer. That'd be fun to get too. But let's get the work first. I just need some room to do it. So I'm going to have to make some room here. We need some room. If you just sort of woke up from a daydream, we're doing problem 3105. It's a polytropic process with air. We've done the device sketch. We've drawn the process on a PV diagram. But to find the work per mass, we're going to use this wonderful equation that we cooked up earlier. Now, what do I put in the denominator again? Does anybody know?
The 1 minus n.
Okay, great. Well, let's do it. Now, what did we say P2 was? That's 200 kilopascals. And what did we say V2 was? 1.485. And then we're going to subtract P1, which is 2200. And V1 is 0.2348. Then we're going to divide by 1 minus 1.3. Okay, go for it. Put all that in there, please, and we'll get our work done per mass. Well, I got an answer. I don't know if it's right or not, but I got an answer. Let me ask some of you guys what you got. We'll see if it's the same thing I got. How about my friend Nathan? Nathan, what'd you get when you did this, Nathan?
731.87 kilojoules over.
That's exactly what I got. I got a work per mass is 731, I don't know, you can round it off to 0.9 kilojoules per kilogram. Now let's check our work. This is a new concept I introduced a number of semesters ago to my students. It's called checking your work to see if it's any good. Now you know that P2V2 is equal to RT2. So we could get this by going RT2 minus P1V1 is equal to RT1, right? RT1, 1 minus it. Let's see what happens if we do that. Now we know what R is because you're going to memorize that. It's 0.287. And we know what T2 is, and we know what T1 is. So just subtract them. Let me do that. 1035 is T2. And when you subtract 1800, well, actually, I get a minus 765 Kelvin. It got colder, you know what? And then we divide through by 1 minus 1.3. Put that in your calculators where K is 0.2287. Yeah, put that in there and let's see what happens. Boy, Juve, you know what? When I did that, I'm coming up with 731.9. Same answer I got here. Hey, that's good. I think we did that quite well. We've got the work. That means the area underneath this graph here is equal to 731.9 kilojoules per kilogram. So far, so good. Any comments or questions on that? Oh, gee, we're running out of time. Oh, no. No, we aren't. No, we aren't. We are not running out of time. We got till 12:20, don't we? Yeah, good deal. Yeah, oh, wonderful. We got till 12:20. I was thinking, oh, gee, class will be over here. But no, we got time. They wanted us to find the heat transfer per mass. Now, they called it the specific heat transfer. If I only had a little room, we could show you that. Let me sacrifice my device sketches. I need some room over here. They want Q. They want us to find little q. Now, does anybody have any ideas on how we could go about finding that little q? I'm open. I'm listening for ideas. Go ahead. Somebody tell me an idea to find out the heat transfer per mass.
You mean the formula?
Yeah, give me a formula to find the heat transfer per mass.
I think it will be Q2 equal MC V parentheses, open parentheses, T2 minus T1 close parentheses plus W2.
Say that slowly, Reagan. I'll write it. Say it slowly so I can understand what you're saying.
1 Q2
1Q2.
equal MCV,
MCV,
open parenthesis,
like that.
yeah, and T2 minus T1, I mean T2, not C,
C2,
T,
C2,
no, T2,
T2
yes,
minus T1.
T1, and you close parenthesis,
Yeah.
plus 1W2.
Yeah, I think I understand now what Reagan's telling me. That 1 and 2, they go down there. They're subscripts, aren't they?
Yes, they're like that, yeah.
Yeah, now I got lost on this MCV thing. What's that?
The M stands, I think the M will be, I don't know if we find the mass on the beginning of the.
Oh, the mass. Yeah,
Yeah.
that's the mass. It's a little m, isn't it?
Yeah, little M, yeah.
And this V is a subscript.
Yes.
You know what? I think Reagan has given us the correct formula. I didn't understand it, but now I think it's correct. Okay, now Reagan,
Yes.
what you've just done is the first law of thermodynamics, which goes like this. Only you did it in big letters, Reagan. You've got a big Q and a big W, and with that M in there, that's going to give you the change in internal energy. But with little letters, you don't need to worry about the M, and that's going to be a little q, and that'll be a little w. What Reagan gave me was the first law of thermodynamics, but I want you to use it in little letters. And see what this is equal to is C sub V delta T. This is Q minus little w. But yeah, Reagan, that was good. That was good. It was correct. But I want you to work with these little letters. Now, the thing is, we know this. We know this. We know the change in temperature. We can look this up. In fact, for air, I think I have that memorized. It's, is it 0.717 kilojoules per kilogram Kelvin? We probably should look that up. Go to the back and look up that C sub V for me for air, or make sure I'm not lying to you. Go to the back. We're going to look it up here. C sub V is at 0.717. Yay, I got that right. Good. Now the change in temperature, I know what that is too. Well, it's final minus initial. Now, Reagan wrote it as T2 minus T1, where these really are subscripts. Here, I'll write it like that. Is this going to show up? I think so. T2 is 1035. T1 is 1800 equals Q minus W. Now the little W we got, it's the 731.9. Need a little room here. 731.9 kilojoules per kilogram. Now let me box this one up for you. This was the same formula that Reagan gave us. It's just with the per mass amounts. It's kilojoules per kilogram. See, it's kilojoules per kilogram. and the Kelvins cancel. Ah, but look, you can get the heat transfer that way, can't you? All right. Can you all read that okay? I think so. Yeah. All right, plug all that in and find the heat transfer for me. Go ahead, I'll give you a minute or so. We're going to get the heat transfer. Well, I got the heat transfer, but I need some room to write it down here. Let me erase all this. You don't need it. I got the heat transfer per mass. Now here's what I got. I got 183.4 kilojoules per kilogram, and I'll wait for my uh-huhs. I need 2 or 3 uh-huhs. If I'm right, I might not be right.
Uh-huh.
There's one. I need a couple more to feel good, because we could both be wrong. Dang, I erased my device sketch, didn't I?
I have a question.
Yes, go ahead.
This is Brian, by the way.
This is Brian. Talking to your microphone, Brian.
Yes, sir. I'll get as close as I can. Is that temperature T2? Is that 1035 or is that 103.5?
No, it's 1035.
Okay. I don't know why I thought it was the other one. Okay, thank you.
Now remember, that's Kelvin. 103 Kelvin would be very, very cold.
Okay.
Okay. All right. Now let me draw you that device sketch. I erased it, doggone it. But remember, it was like this, and we had a heavy weight on it, didn't we? State 1. State 2, we took the weight off, the volume went up, pressure went down, temperature went down. But according to our work here, we're getting a positive heat transfer. What that means is we are transferring energy by heat into our air inside our piston cylinder. If it weren't for that, our final temperature would have been a lot colder. Do you understand? It would have been colder. But because of our transferring some heat energy into the cylinder, it's not as cold as it would have been. I don't know if that makes a lick of sense, but hopefully it will eventually. So we got that. We whipped that problem. We did great.
Professor, this is Nathan. So are you saying that from process 1 to process 2 that we are getting, we're increasing Q
We are transferring heat energy into our cylinder. 183.4 kilojoules per kilogram is being transferred into our air in the cylinder, Nathan. That's what we're saying.
Okay, I'll just think about it a little bit more. That's fine.
Well, I think we did everything right, and let's do another one. That was fun, wasn't it? Let's do another one. We got 20 minutes and we can do another one. Here we go. I'm going to erase all this unless you have another comment or question. Nathan's struggling with trying to understand that. Okay, well, let's do another one. Here we go. Okay, now this is problem 3106. Uh, 3106, it's R410A. That's what I have in my house, air conditioner. 3106. Okay, this says saturated vapor R410A at -10 in a piston cylinder. It's compressed to a pressure of 1200. In a polytropic process with N equal 1.5, find the final temperature, process work, and heat transfer. Okay. Well, why don't we draw the device sketch? That'd be fun. Here we go. This will be state 1, this will be state 2. And we start off with -10, and we're going to compress it. All right. So I get the feeling we probably put some weight on that, and that compresses it down here. Put the weight on there. This is state 2. This is state 1. We're going to compress it. Now it starts off at -10 degrees Celsius. My guess is it's going to get hotter. Isn't that what happens? Now they told us though that it starts off at saturated vapor. Saturated vapor. Now we know where that is on a PV diagram. We're dealing with a refrigerant. It has a vapor dome. We're located here at saturated vapor, -10. Go back to the back and find the R410A table. I'm looking in the back here, R410A. Yeah, I found it. And I told you guys, you always go to the vapor dome table first, and you'll discover that -10's right in the middle of the table. So let me draw my isotherm there. And you know how they go like this. There's your -10 degrees Celsius isotherm. And we know what this pressure is right here. My table says 573.1. Now I need you to look in your table. Those are kilopascals. And see if you can find 573.1 at -10 degrees Celsius. Can you find it? If so, say, uh-huh.
Uh-huh.
Hey, there's one. I need somebody else. Feel good about it. Yeah, there's one. Excellent. Good deal. Let's write down some stuff, shall we? How about the specific volume, for instance? The specific volume at state 1 is 0.04553. We might also look at the specific internal energy. Let's get that while we're at it. And check me and make sure I get the right numbers here. I get 249.69. And if I got the wrong numbers, sing out, let me know. You're supposed to put units on this stuff. Okay. Well, that's good. And now what? Let me keep reading here. We're doing 3106. And saturated vapor, minus 10, mass 0.6 kilograms. Let me write that down. 0.6 kilograms. All right. It's compressed to a pressure of 1200 kilopascals. Hey, you know what? This is 573.1 kilopascals. But now when you put that heavy weight on there, we've got 1200 kilopascals. We've upped the pressure, haven't we? Pressure went up. In a polytropic process, N equals 1.5. We need to write that down someplace. Okay, find the final temperature, etc. Well, what do we know about polytropic processes? Let me write this down. We know that P1 V1 to the 1.5 equals P2 V2 to the 1.5. Now, do we know P1? Well, yeah. Yeah, we do. Do we know V1? Well, yeah. Yeah, we do. Look, there's P1 and there's V1. Yeah, we know those. Do we know P2? Yeah, look at here. Yeah, we know V. Oh, look at here. We have an equation with only one unknown. Now, I'm going to shut up for 2 minutes. I know you can do this. You can find V2. I'm going to shut up. I want to see if you can find V2. On your mark, get set, go. Well, I think I know what V2 is, but let me ask some of my students here. What about my student, what about my student, Bryce? Bryce, unmute and say hi, Bryce.
Hi, Bryce.
Okay. Bryce, did I give you enough time to get the V2?
I've got 0.0278 cubic meters
That-
per kilogram.
That's what I got. I got 0.0278, maybe 2 cubic meters per kilogram. Okay, good going, Bryce. Proud of you. Now, do I need to go through that for anybody? If you're having trouble, I'll go through it. Just speak up. Well, nobody spoke up, so I guess you can do it. Yeah, I bet you can. Good for you. We need to find that. Now we know the pressure went up to 1200. Well, see, 1200's in here someplace. Let me show you where 1200 is. There we go. There's 1200 kilopascal. We know we're on the 12. We know we're on that 1200 someplace. We just need to find out where. Well, you can go to the Vapor Dome. They don't have a 1200, but you can look at the VG there. And our V2 is bigger than any of theirs. So here's what's going to happen. This is going to come up here. And state 2 is going to be in the superheated vapor region. It will not be in the Vapor Dome because I can tell by looking at the values for VG around 1200 in that table, and they're smaller than this V2. So what we're going to do is we're going to go to superheated vapor and look up 1200. Shop with me. There's 1200. Now, right now, I need a little room here. We're in the 1200 kilopascal superheated vapor table. And what we want is 0.02782. 0.027. You know what? It's between 40 and 60 degrees. Between 40 and 60 degrees Celsius. The V, we need 0.0. The V, the little V is 0.02563, and at 60 it's 0.02830, and the U, if you needed the U, it's the little U thing is 281.72 and 299.00. Okay. And see, what we want is 0.02782. 0.02782. And we can get the temperature. And we can get the specific internal energy. Now, what did they want us to get? I got lost here. Let me go back and see what they wanted. We're doing 3106. And find the final temperature. Well, they want us to find the temperature. Well, we can do it. All we got to do is interpolate this, and we can get it'll be between 40 and 60. I think it'll be closer to 60. And then they want the work and heat transfer. Well, okay. We have 6 minutes left. We might make it. I don't know. It's going to be close, though. We're going to interpolate this and get the final temperature. But while you're at it, get this U, because we're going to need it for the first law, okay? Go ahead. I'm going to interpolate, get the temperature. You do it. Here goes. Well, I got the temperature. I think it's 56.4. Pretty sure, but I'm not 100% sure. Did anybody get 56.4 degrees Celsius for the temperature at state 2?
Yes.
Yeah, I heard
That's
a
what I
yeah.
got.
Yay, there's 2 of us. Good going. Now I can show you what the isotherm looks like that goes through there. It goes like this. That's your 56.4 degrees Celsius isotherm. So our temperature went up. Now, how come it went up? Well, because we're compressing. When you compress, it gets hotter. Yeah, it gets hotter. So now the new temperature is 56. It was minus 10. It was minus 10. And now it's 56.4 degrees Celsius. Now let me just outline for you how you would get the. I've got 3 minutes left. I don't have time to do it, but I can outline it for you. Show you how to go about it. Do we have any room here? Not much. A little bit. Here's what you'd do. You'd go P1V1 to the 1.5 equals P2V2 to the 1.5. Now wait a minute. No, we already did that. Never mind. That's not what I want. Here's what you'd do. Little w is equal to P2V2 to the no, just like that, minus P1V1 all over 1 minus 1.5. Now I'll show you a dirty little trick that might help you. No, I won't show you that dirty little trick. What I was going to show you is that P2V2 is equal to RT2, but you can't use it here. This is not an ideal gas. You're going to have to stay with the P2 and the V2 and subtract the P1 and the V1. It's not an ideal gas. You can't put PV equals RT on this stuff. But look, we know all of it. We know P2, yeah, 1200. We know V2, it's sitting right here. We know P1, it's right here. We know V1, it's right here. That was V1, wasn't it? I think so. Yeah, you could get little W. You could get the work. They wanted the work. Oh, gee, we have 1 minute left. Now, how about the heat transfer? I wish we had time to do that, but here's how you do it. I just need some room. You write this equation here. Now, I just showed you how to get the little w. And we know everything. We can get it. Delta U. Now, before what we did was we went C sub V delta T, but we can't do that here because that's an ideal gas equation. You can't use it. It's not an ideal gas. But you can get U2 minus U1. See, we could get U2 by interpolating. I didn't have time to do it. And U1, look, we got U1, it's sitting right here. So we can get that. If you know the work per mass and you know the specific, or the change in specific internal energy, you can get the heat transfer. It'd be interesting to get that and just see whether it's going in or out, but we don't have, oh, it's sad, but we don't have time. We're gonna have to quit. Have you noticed how the time goes by so quickly when you're having fun? Any last words? This is your last chance to say anything until, what, Thursday at 11? Go for it, anybody?
So U2 is from interpolation, that's what you said?
That's right. U2 is from interpolation.
Okay.
Yeah. I wish we had time, but we don't have time for everything. We'll do the best we can. Anybody else? Last call going. Okay, bye-bye, students. Till next time.
Bye. Have a
So
good
long.
day.
Have a good day.
Yeah, you
Bye.
too. Bye-bye. Have fun.
You.